Hey everyone, welcome back to the practice exam videos. I'm Virginia, and if you need to contact me, you can do so at the email below. And this is going to be the practice exam 4A, and it's a final, which means that we're finally done. Okay, and so, again, it's best if, when you're using these videos, to have paper, to have a pencil, a Chem 110 approved calculator so you know how to use it come exam time, and to actually work through the problems yourself, not just watch me do them. So the first question is asking us about a new element, nitnium, and I've underlined some of the properties that they've measured for nitnium. They found that it's brittle, has a really high melting point, but isn't a good conductor of electricity. So, most metals are malleable or can be molded and bent, like gold and copper. And metals generally conduct electricity well, too. So we can get rid of metals. For these problems where you're identifying solids, it's really just best to go through and do some definitions, because high melting points are typical of ionic compounds. Okay. And so these are compounds like salts and stuff, and we think of salts as being very brittle also, and not conducting electricity well. And so I would just spend some time with the notes on the ebook, relearning some of these and reviewing the types of metals and their properties. So this is an ionic compound. Okay. For number 2, they're asking us which of the following ligands can be classified as bidentate. And so we know that the prefix bi means 2. And so we're trying to figure out what can coordinate in 2 sites with a metal. And so we know metals are positively charged. So we'll have some metal, and often, not all the time, but frequently they're 2+. And so we want to look for something that has lone pairs that can butt up against this metal ion in some kind of double fashion. So we want to look for something that could do this kind of rearrangement, and that would make it bidentate. So if we look at ammonia in the first option, this is a good ligand because it has the lone pair, but it only has one. So we would consider this monodentate because there's no way for it to have more than one lone pair come grab onto the metal. Whereas number 2, this is that En molecule that we've been hearing about. And this can wrap around, and both the lone pairs on each nitrogen, so the lone pairs on each nitrogen, are able to get up against the metal. So this one is bidentate. With this carbon monoxide, one of the lone pairs could get up against the metal, but then there's no way for it to twist around or anything to have a second coordination site. Okay, so the geometry of this keeps that one from happening. This one's also mono. Okay. Then we get to the 4th option. And you guys aren't expected to be able to identify this, but this is the EDTA molecule that we've talked a lot about. We know that EDTA has a coordination number of 6, and that's because it just has so many different ways that it can kind of claw on to the metal and wrap around it. Okay, so this is more than bidentate. Okay. And in number 5, these negatively charged oxygens would each be able to butt up against some metal and coordinate. And these ones would stick up into space, away from the metal. So we would have two possible coordination sites, making this also bidentate. Okay, so the answer here is E. For number 3, we have a strong base and water, and they just want us to write out the reaction for this. So we know that the whole thing about what makes a strong base is that it's able to pull a hydrogen, take a hydrogen from water. So we'll have this H minus taking an H plus from the water, making H2, and that leaves behind OH minus. Okay. And so it's as simple as that, just a classic strong base reaction. And so the answer here ends up being B. So pretty straightforward, don't overthink it. Okay, a buckyball is an allotrope of carbon. What kind of solid would this make? Buckyballs are pretty awesome. They just are like molecular soccer balls, kind of. And they're just hilarious. So, anyway, C60, you can eliminate atomic right off the bat because it's not just one atom. Carbon isn't a metal, so we can eliminate metallic as an option. It's not ionic, so that one's out. And so this one will end up being molecular. What you end up with basically will be a bunch of soccer balls packed together. And so this isn't a network covalent because it's not forming like a continuous sheet of atoms. Okay. And so it's not one of the ones we keep in mind like SiO2 or graphite. Okay. So it might be worth committing some of these network covalents to mind so you can identify them more easily. But this is just going to be molecular because you have a bunch of nonmetals. Okay, porphyrin ligand. If you are really interested in porphyrin rings, there's a lot of people at Penn State who do research on these metal complexes and proteins. But anyway, they're asking us what the charge on a porphyrin ring is. So if we look in at the inside, we can identify some metal ions at the center. And so you can see how they have those little twos, or the double lines next to them. And what that means is just they have a +2 charge. So if the metals have a +2 charge, and they tell us that our complex is neutral, then it's as simple as thinking that the porphyrin must be -2 to make the overall charge be 0. Okay. So the answer here is just C. Nothing too crazy, but you do have to be able to find those metals in there and see that they're +2 charged. Okay. In question 6, we're using the spectrochemical series. And they're asking us which would absorb light of the shortest wavelength. Okay, so shortest wavelength we know is highest energy from this relationship. So if we have a shorter wavelength, higher energy. Okay, and what the spectrochemical series tells us is that these are strong field ligands on the right. So they'll have a big delta. Whereas these are weak field on the left. And they'll have a smaller delta. And this delta refers to the energy gap between our two sets of d orbitals. And it tells us how much energy it would take to promote an electron from one to the higher level. Okay. So we want to pick something that's furthest on the right in our series, because that would give us the biggest energy, we'll have the biggest delta, smallest wavelength. So we just look at all the options here and the ligands associated. And we can see that the cyanide is furthest to the right, so it will be the strongest field and give us that biggest energy gap. So we would need a shorter wavelength of energy to promote it. Okay, so that one's just going to be B. Okay. Now we have a Mo theory problem. And they've given us the nitrosonium ion. So I've gone ahead and drawn the large diagram here. So if you have the data sheet out, which you should, there's the two diagrams. And so you would just use the large one, because they tell us. Okay. So I'm going to count the electrons. We have our nitrogen electrons of 7. We've 8 from the oxygen. So here I have total electrons because I have all of the orbitals drawn. And we have a positive charge, so we're going to, even though this would be 15 electrons, we'll have lost one. So we'll have 14 total electrons to account for. So we fill them in low. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Share before you pair. 13, 14. Okay. So I filled out the diagram. So we have to think about bond order. So we can remember that bond order, or everyone's favorite abbreviation of BO, is equal to the number of electrons in bonding minus the number of electrons in anti-bonding orbitals divided by 2. So we're just going to count. In our bonding orbitals, we have 2, 4, 6, 8, 10. And in our non-bonding orbitals, we have 2, 4. So we'll have 6 divided by 2 for a bond order of 3. And so just remember that our anti-bonding orbitals are the ones with the stars. Okay. They're the higher energy orbitals. They have the node where electrons can exist, and we mark them with the star. Okay, so E is the answer there. Okay. For number 8, they're asking us for the pH of a solution. We have some acetic acid and some chacuna. And they give us the Ka. Okay. So I've written here what happens when you just put acetic acid in water. And we know it acts as an acid and deprotonates. And so what we see in this reaction is that we have acetic acid and its conjugate. And in the problem we have acetic acid and its conjugate. And whenever that happens, what do we have? A buffer! Okay, because we have something that's weak, and we have its conjugate. And so the nice thing about buffers is that we can use this Henderson-Hasselbalch equation, which I've written here, to get the pH. And it's simpler than doing an ice table. So we need to start by figuring out what our pKa is. So we know that pKa is going to be equal to the negative log of the Ka, which is this 1.8 times 10 to the negative 5. And it ends up being 4.74. Okay, easy enough. So then we go to use this equation. We use 4.74 for the pKa. Now plus the log of our base divided by acid. And another thing that's nice about this equation, besides avoiding an ice table, is that you can either use moles or you can use concentration, as long as it's the same units for both. So here I can use the 0.2 molar of the base, or the chacuna, divided by the 0.55 molar from the acetic acid. And when you go through and evaluate this, it ends up being 4.30 for the pH. Okay, and that's it. So if you identify the buffer, this problem becomes a lot simpler because then you can just use the Henderson-Hasselbalch equation. Okay. We want the KEQ for this reaction, and that's all they give us. It's not a ton of information. But hopefully you all now are seasoned electrochemistry experts and can identify this as a redox reaction. So I did that, and I went ahead and wrote out the half reactions associated. So we have this reduction where copper plus gains an electron to become copper solid, and we also have it for when the copper plus loses an electron, it's oxidized to copper 2 plus. Okay, so I've written those two half reactions, and we can use the table of potentials, which you all have out right next to you right now, to figure out what the standard reduction potentials are, or the standard potentials. So if you just look at the table for this copper reduction, you want to pick the right one, but it's 0.521 volts. Okay. And on the table, you have to flip the reaction to get the oxidation reaction. And when you do that, you have to flip the sign of the value. So when you find this reaction, flip the sign, it ends up being a negative 0.153 volts. And we care about the E cell, which will be 0.368 volts.
Hi.
Hi.
How are you?
Okay, how are you? Okay, I got rid of Todd. Sorry. So we get our E naught cell from this. And this is useful because we can relate it to KEQ using one of the equations from the data sheet. So we have E naught equal to 0.0592 over N times the log of K. Okay, where N is the number of electrons, and so in this equation the equations above, you can see it's just 1 electron, which makes the math easier. So then we can say that 0.368 volts is equal to 0.0592 divided by 1 times the log of KEQ. Okay. Do some rearranging, and we find that the log of KEQ is equal to 6.22. 10 to the power of 6.22 gives us our KEQ, which is 1.65 times 10 to the 6th. A big guy. That's a big one. Definitely products favored. Okay, and that answer is just D there. Okay, so they don't give us a lot to work with at the beginning, but that's okay, because we can slow down, see that this is a redox reaction, split it in half reactions, and then we'll be good to go.